Okay, good morning and happy snow day. It'd be fitting if we were talking about heterogeneous nucleation of crystals today, but that happens in 2 weeks. Hopefully there won't be another pile of snow then. But today's topic is wetting and small-scale fluid flows. So I pulled the topic on wetting, which we didn't get to last time, into today's lecture, and I actually think it's a better fit in combination with discussion of fluid flows, because we'll talk about interactions of fluids with surfaces having small-scale dimensions and small-scale texture. And there's a lot for us to cover today. We'll get through as much as we can. My only announcement is that I've posted the description of the video assignment. This is what, in comparison to past terms, is taking place at the literature reviews. And take a look. In short, we're asking you to form a team of 3, and this can be whoever you want, and maybe even the same people you work with on the project, and to choose one of the 14 topics that we've listed, which relate to the lectures pretty much through now, maybe considering a couple more topics, but generally before the lectures before spring break, and to do whatever you want to make a 5-minute video to talk about it. And this is due in about a month. Take a look. You can sign up on a Google spreadsheet that I put up, all first come, first serve, 1 team per topic, and I'll talk a bit more about it in detail and answer any questions at the beginning of lecture on Monday. Okay. So last time we talked about surface energy and melting as an extension or building upon our previous discussion of intermolecular and surface forces. And we first talked about kind of the subtle difference between the interaction energy, like the van der Waals energy, and the surface energy. And we saw the surface energy is essentially the energy needed to take a material and to separate it into 2 half spaces. And this has a direct relation to the melting point of a material, because as you can imagine, if there's stronger interactions among the atoms in the material, then it takes more energy to melt it and more energy to separate it. And we came up with a relatively simple expression for 2 planar surfaces, and we defined the surface energy of a flat surface as being proportional to the Hamaker constant divided by a constant, a numerical constant, and divided by a square of a factor d0, which we then related to the lattice spacing of the material. And this is the surface energy, which is in units of energy per area, or say joules per square meter. And then we use this parameter, the surface energy, to derive a model based on simple thermodynamics, basically on free energy changes upon melting, for melting of a spherical nanoparticle that looked like so. And remember, we had a number of assumptions in terms of perfect wetting of the liquid layer and having no density or volume changes in the system. But that got us to a relation that actually is quite accurate and observed experimentally, that the melting point of a small structure, in this case ideally a sphere, is proportional to the melting point of the bulk material times a factor which gets smaller as the radius of the particle gets bigger. And you see there are some material properties here that relate to the bulk, meaning the surface energy and the latent heat. And we saw more qualitatively that we can kind of derive this for different shapes, and this has some implications for processing of nanostructures. And what I want to talk about today is how we can now build upon our understanding of wetting, or of surface energy, to understand a bit about how surface texture and surface energy relates to the wetting behavior, basically if liquids wet surfaces or they do not. And then we're going to talk about effects of micro nanoscale textures on fluid flows. And the idea here is that I think there are some analogies to what we previously defined as classical and quantum size effects about how we need to think about fluid flows when the dimension of our system gets small. And we're going to talk about what is considered the breakdown of the no-slip condition at solid surfaces when you have a small-scale system. And remember, if you took fluid mechanics in the past, that when you derived, for example, the flow over a surface or the flow through a pipe, we always applied the no-slip boundary condition, i.e. we assume that the molecules at the wall have a 0 velocity. Well, that's not actually true, but when we model the flow through a macroscopic thing like a macroscopic pipe, and we'll define the dimensional limits in a while, there is actually a bit of slip. But because the interactions within the fluid, like molecules colliding with molecules within the fluid, are so much more important than the interactions between the molecules and the wall, it doesn't really matter whether we say there's slip or not. And if we say there's no slip at that scale, it's a lot easier to solve the problem. But it turns out, much analogous to thinking about boundary scattering of heat carriers and scattering of electrons going through materials. When we get down to small scales, it turns out that these interactions with the wall are important, and it makes a big difference, for example, whether or not we consider whether the flow is slipping past the wall. And in fact, some materials, for example, carbon nanotubes, exhibit a lot more slip than other materials, and that leads to some interesting observations about their properties and also understanding of slip. And although it's pretty difficult, we'll talk about a bit of research that has led to experimental understandings of slip flows of gases and liquids through microchannels and through nanotubes, and that'll be our last topic. So there are a bunch of papers to read. I pulled the Tuteja reading up from last time, so it's now in this lectures folder. And then I have two papers and one excerpt from a book talking about basically small-scale gas and liquid flows. Karniadakis, the excerpt I took from this book called Microflows, which is a nice book on small-scale flows in general. The excerpt I took just talks about the reasons why we need to consider different flow behavior in small-scale geometries. And then the Archillik paper talks about the way we model slip flows through microchannels, and then discusses experiments used to measure things like the coefficient of slip, basically how much a gas molecule will slip against a wall inside a channel. And then the Eichel paper talks a bit about liquid slip, and we'll understand the different ways we think about gaseous slip and liquid slip a bit later. And then there are a couple of extra readings that talk about slip flows and measurements and modeling of flows through carbon nanotubes. I think for me, it's a really interesting topic, and we'll just cover a bit about this in lecture. And in the homework set, I ask you to reference this paper to obtain a number that you'll use in your calculation. So this is the paper that I mean in the description to problem, I think it's problem 1 in the problem set 2. Okay, so first I'm going to talk a bit about wetting, and you've probably seen wetting before in fluid mechanics or in other classes. And the thing that may be a new concept that I want to introduce is that the ability to engineer surfaces chemically and physically is leading to some understanding of how natural surfaces behave and how to design surfaces so they, for example, will attract liquids or repel liquids. And when I say attract, I mean having a surface that wets a liquid or a surface that is wetted by a liquid like so, which is quantitatively referred to as having a small contact angle, because classically the contact angle theta is measured through the fluid from the substrate up to the edge of the meniscus here, or to engineer surfaces so the liquids don't like them, or they don't like the liquids. And that is the case where you have a large contact angle, and there's a large angle if you measure through the fluid like so. So the liquid, the wetting in terms of a formal definition is the ability of a liquid to maintain contact with a solid surface. And as you can imagine, what governs wetting behavior? Well, it's got to be the interactions between the molecules in the liquid and the molecules in the solid. And imagine if you have a drop of liquid, which you can consider like a particle or a spherical body. There are cohesive interactions within the liquid, and then there are adhesive interactions between the liquid and the other body, the other material. So in the case of a liquid and solid, the contact angle between the liquid and the solid is going to be determined by this overall free energy balance, whether depending on what creates a net decrease in energy of the system. For example, if the solid surface has a very high surface energy and the liquid surface has a very low surface energy, then it's likely energetically favorable for the liquid to wet the solid and therefore to reduce the net free energy of the system. If the opposite is true, if the liquid has a very high surface energy, then it's going to want to minimize its own surface energy over exposing more solid surface. And that, from a real first level, is kind of how you could think about whether a liquid will wet a surface or not. And so if you look at contact angles, having a small contact angle, something smaller than 90, is generally considered a wetting surface or a wetting case, and having a contact angle greater than 90 with the ultimate limit of 180 is considered having a non-wetting case. And if you have a contact angle that's in the hundreds, say above 150, then the droplet looks pretty spherical, and it's perhaps likely to roll off the surface when you tilt it. because also depending on the size of the droplet, certainly not at the nanoscale, but like in the case of droplets you might see on leaves outside in a rainstorm, the gravitational effects are also important. So if you tip the leaf, the droplet might roll off because of its weight, and that actually is exerting a force that may or may not be balanced by the strength of the interactions between the two. And if there's not a lot of attraction between the liquid and the solid, then it's going to be more likely to roll off. And in terms of what governs surface energy, we could see from what we understand now that solids that are strongly bonded have high surface energies, and you would expect that they have high, large van der Waals forces with other solids, and solids that are weakly bonded probably have lower surface energies and have lesser van der Waals interactions, and that can relate also to wetting behavior in general. And one of the real practical challenges has been that as a result, it's been hard to design surfaces that are non-wetting to liquids with low surface energy, because liquids with low surface energy will be much happier to spread out and cover a surface because that will possibly decrease the overall free energy of the system, and that has practical implications for things like cleaning up oil spills, because things like oils and solvents have low surface energy, and also is important for things like separation of liquids with different surface energies. So I just wanted to show you a couple of videos. One of the things that's done when people study interfaces between solids and liquids is you want to say measure the contact angle, and you sometimes have what's called a contact angle goniometer that has your surface and just has a good light source and a good camera and lets you get a picture of the situation. Let's look at a video that compares the behavior of a non-wetting surface to the behavior of a wetting surface. And this is taken with a high-speed camera and slowed down. So these sometimes just make fun pictures that people show when they show a surface is non-wetting, but in this case you can see that the solid and the liquid don't attract so well, and the momentum of the liquid droplet coming in is reflected somewhat by the surface, and the liquid in fact kind of rolls off and then spills off to the side. And it turns out that was just a film of carbon nanotubes that was grown on a silicon substrate. And then if we look at a similar video taken with a silicon substrate uncoated, then there's a big difference. So the same droplet doesn't bounce up and wets a lot more easily. And silicon typically has a native oxide on it, and unless that's etched, for example, using HF, using hydrofluoric acid, typically in air it'll become hydrophilic, and it'll have a low contact angle, hydrophilic meaning that the substrate likes water. So one of the motivations in figuring out how we might engineer surfaces using chemistry and texture to basically play with the interactions comes from looking at things in nature. And there's a very classic example that's been talked about a lot and mimicked a lot of the lotus leaf, where if there's a rainstorm and you look at a lotus leaf, you see that the water droplets bead up. So that is a non-wetting surface. It's somehow engineered by the plant to really repel water, and you take the leaf and you tip it and the water rolls off very nicely. So it's like having a pair of pants where if you spill your drink on it, the liquid rolls quite right off. And there's an interesting comparison between the lotus leaf and the leaf of a rose petal, where that surface is also non-wetting. But in the case of a rose petal, if you flip the surface over so the droplet is against gravity, the droplet doesn't roll off, and it stands, and it depends on the size and so on. But in this example, we're seeing that the droplet isn't rolling off the surface, as in the case of the lotus leaf. And basically what these examples tell us is that the behavior of surfaces in response to liquids can be controlled by engineering both the surface energies of the relative materials, for example, the surface energy of the material that the surface is made of, and the topography, because the topography is a way to play with the local contact angle and to manipulate the contact area. And you can imagine that, like, if you have, say, a corrugated surface with twice the total area than a flat surface, that might do different things with the wetting behavior than if you just had a flat surface. Or you can kind of play games exchanging surface area for surface energy in that regard. And in the case of the lotus leaf, this is a higher magnification image of smaller droplets. This might have been taken in an environmental SEM where you can add a little water vapor to the atmosphere. And you can see that the texture here is these little huts on a flat surface. And there's a similar thing going on here in the case of the rose petal, where there are these little huts. So there is certainly some nanoscale texture going on here. And the interesting thing that's been found out is that this surface is highly non-wetting, even though the actual material that this is made of is slightly in the wetting regime. So if you had a flat surface made out of this material, it would have a contact angle with water slightly less than 90 degrees. So solely the effect of the texture of the surface on its interactions with the droplet is what makes it non-wetting. And so when people look at the geometric dependence of how wetting depends on geometry, they typically define two different states when you have a textured surface. So first, if you have the simplest case is if you have a flat surface between a solid and a liquid and then a surrounding medium, which we'll for now say is a gas, and you define the contact angle like so. However, if you have a textured surface, and this can be something that's regularly textured, like something etched with micropillars, or it can be something that's less regularly textured, like the natural surfaces we just saw, you have to consider the properties of this composite interface, basically how the liquid interacts with all the surface structures that you have. And there are two states, and the state where the liquid is penetrating you could say down to the subsurface here and basically wetting all of the surface area available is what's called the Wenzel state. And when the liquid is sitting up above the texture, it's what's called the Cassie or Cassie-Baxter state. And you can go in and look up there are ways you can derive the contact angles in both of these cases depending on the roughness and surface energy. But basically what happens is if you manipulate this texture in response to the surface energies of the materials that the surfaces are made of, you can control the contact angle between the two. And there are ways also, for example, to observe the migration and wetting of surfaces at relatively small scales. And this is a picture of a study of the wetting behavior of a surface inside an environmental SEM, where they're condensing water droplets on the surface while watching it happen. So this is happening at low pressure, and you're just letting a little bit of water vapor into the chamber, and the droplets are condensing. And for example, you can see here how some droplets nucleate on the bottom surface and are really too small to cover a number of pillars, and other droplets may nucleate on the top surface and then grow, you could say, into larger droplets and perhaps will eventually end up covering the whole and being non-wetting on the top. And we really haven't talked yet about why changing this texture makes such a difference to the liquid. That's going to depend on the particular conditions of the system. But what's been found in the case of the two flowers that we saw before is that what governs whether or not that droplet rolls off the rose petal or stays on the rose petal versus rolls off the lotus leaf is how the surface of the liquid actually conforms or doesn't conform to the structures themselves. So what's been found is that the texture of the surface in the case of the rose petal gives an overall non-wetting shape to the droplet, but at the interface, the droplet wets the surface very closely. And in the case of the lotus leaf, it's also a non-wetting behavior for the droplet, but and with that, the liquid stays sort of above the pillars, and this gives a low adhesion of the liquid to the surface, and then the droplet runs off more easily. Whereas here, you could say it's more stuck. And depending on the size of the droplet, if it's small enough, it's going to resist its force of gravity as you tip the leaf over. And for example, there are ways to, for example, control the texture of surfaces and to control their coating. This is an example of where a vertical film of carbon nanotubes was grown and then coated by CVD, by a vapor deposition process, by a thin layer of Teflon, which has a very low surface energy. And then they were able to get an extremely hydrophobic surface, taking advantage of the small, overall surface area of the tips here. You can imagine that you would need to deform the liquid interface a lot for the liquid to penetrate this forest, and that's going to be energetically very expensive. So it's favorable for the liquid to stay up above, on top, and also the low surface energy of the Teflon relative to the surface energy of water is going to promote the surface to want to repel the droplet, and it turns out that you get a surface that is extremely hydrophobic. And this was interesting because it combined this effect of texture and the effect of the chemistry of the coating, the low surface energy of the molecule itself, and also at that time was one of the most hydrophobic synthetic surfaces observed. Typically, people say something is hydrophobic when the contact angle is greater than 90, but in this case, it was essentially spherical. It was almost a perfectly non-wetting surface. And now, more recently, there has been a lot more work in trying to understand how to texture surfaces at the micro-nano scale and quantitatively relate, for example, the shape of the features that you create to how the liquid behaves both at the interface and overall. And for example, in the Tuteja paper, it was shown, it's discussed how these surface textures can be engineered geometrically and chemically to, for example, now repel oils, so liquids that have very low surface energies. And it turns out that what makes a difference is having a texture that's called a re-entrant texture, so something that basically can't be described by a function that would produce a hill like that. It basically cuts in over itself. So it means it re-enters as you go down. And there is a difference between what we would measure as the contact angle when we say look at the droplet on the surface, and the real contact angle between the liquid and the surface. And so if you looked closely in at this surface, what you would find is that the contact angle between the liquid and each structure is actually quite low. So it's locally wetting the surface. But if you look at the contact angle with reference to the top surface like this, the contact angle is much larger, and therefore you would call it a non-wetting case. And basically understanding how the surface energies work together and what the energetic cost is of moving this liquid interface down toward the surface, creating more interface and deforming the meniscus and so on, lets us predict if the overall texture is going to be wetting or not. And what's been shown is by creating structures like this, which take advantage of this apparent, this kind of difference in contact angle, or let the liquid penetrate a little bit down here, lets them engineer surfaces that have pretty high apparent contact angles. So what we would see from the top here to liquids with a variety of surface tensions, and particularly low surface tensions that are associated with, that are the surface tensions of things like organics, like solvents that are typically hadn't been made non-wetting before. And this is just an SEM image of some of the example surfaces that they made by microfabrication, by etching a silicon wafer such that they undercut a thin film. And these huts sort of allow the fluid to come a bit underneath, but keep it overall have a non-wetting profile and a high apparent contact angle. And as a result of that, the liquid rolls off very easily. And incidentally, this is one of the topics that's up for grabs for the video assignment, is to sort of explain this behavior fundamentally and how surfaces can be engineered to repel both waters and oils, or to repel liquids with a wide variety of surface energies. Okay, are there any questions about that? So for the rest of today, I'm going to talk about fluid flows at the small scale, or how we might have to think a bit differently about gas and liquid flows when we have confinement in the geometry. So we're going to talk a lot about the basic example of having a pipe, and we're going to go from thinking about pipe flow at a large scale to pipe flow at a very small scale. And so, as I said before, a real guiding principle for us is that as the length scale of our pipe, meaning the diameter, the direction perpendicular to the flow, decreases, the molecular interactions with the wall become more frequent compared to molecular interactions within the bulk. Or if I'm a gas molecule going through the fluid, I'm more likely to collide with the wall than I'm going to collide with a molecule in the middle as the diameter goes down. And so these collisions with the walls become more frequent. And also, as we remember from fluid mechanics for pipe flow, the amount of friction through the pipe decreases. So it takes more pressure. There's more pressure drop from the input and the output of a pipe of fixed length as the diameter decreases if you want to put the same amount of flow through it. And that is because the importance of the surface grows. And another thing that's important to consider is that if you have high pressure drops over short lengths, in microscale geometries, and this applies to gas flows, the compressibility is important. Basically, you have to consider the density change as the flow goes through. And we'll see that has a big effect on the prediction we would have for, say, the flow rate through a pipe of a certain geometry. And then the details of the molecular interactions are what determines the relative velocity at the wall, and that's what we're going to call slip. And it turns out that as pipe size gets smaller, the amount of friction increases and the importance of the molecular interactions grows. And that makes us need to abandon the no-slip condition, the condition where we said that molecules don't move relative to the wall. However, it turns out that although smaller pipe size means there's more friction, the presence of slip, which is always there but becomes important to us because we have to consider the wall interactions at the small scale, actually reduces the amount of friction, because a main source of friction through a pipe is the drag that the molecules feel against the wall. If you relax that condition a bit, or if the molecules right against the wall have a higher relative velocity, then the amount of friction through the pipe decreases. And it turns out that these result in significant modifications to, say, the pressure drop we would have across a microchannel, or the pressure drop that we would have across a pipe that would be in the nanometer scale diameter. And as you get smaller and smaller, as the pipes get smaller and smaller, then more interesting and you could say specialized and hard to predict using regular math things happen. But for example, if you confine a fluid inside a pipe that has a diameter that's, say, quite close to the molecular dimension, then you can actually get ordering of molecules inside that pipe and kind of crystallization. One of the classic examples of that is if you have flow through a very small diameter carbon nanotube. It's theorized, and I think has kind of been shown that that water will actually form wires where the molecules will kind of line up according to their natural polarity. And that also occurs because the graphite surface, the surface of the nanotube, is intrinsically hydrophobic. That leads to there being a lot of slip between water and the wall of the nanotube, and also assists in this kind of ordering and crystallization. And even at larger scales, still in the nanoscale, but because of the molecular interactions between the wall, just think of attractive van der Waals forces now, and the molecular interactions between the fluid, there is that attraction, and you can actually have a local ordering of the liquid or some local ordering of the gas between the wall and the fluid. And all these things kind of work together in a particular situation to determine, for our cases, how much slip there is going to be. And we'll be able to capture that by modifying the regular relationship for pipe flow and allowing a slip length or a slip velocity, and then we can relate that to some observations of how much that slip length or slip velocity is in a particular system. And we're going to classify flow regimes based on what we'll call the Knudsen number, and that relates to a mean free path for gas, just as we saw a mean free path for electrons or phonons. So we do classify flow regimes based on this dimensionless number called the Knudsen number. and the Knudsen number is equal to lambda, which is the mean free path. This should be lambda here, divided by L naught, which is our characteristic length scale. So in the case of a pipe of diameter d, our Knudsen number is just lambda divided by the pipe diameter. And in the case of liquids, well, gases and liquids are different because the density of a gas is way less than the density of a liquid. So in the case of gases, we define the Knudsen number based on the mean free path, but in the case of liquids, we define it based on a slip length which we'll define as b. And we'll show what the slip length actually means in a few slides. And in the case of gases, we can relate the mean free path to the ideal gas law and properties of the gas based on the kinetic theory of gases. And what we can come up with based on this definition of the Knudsen number for a particular gas is a plot that tells us what flow regime we are in as a function of our characteristic length scale, our dimension of the system, and the relative density of the gas. So on the x-axis, we have a quantity n divided by n naught, and this is just the relative number density as compared to air at STP, so as normalized with the corresponding atmospheric conditions. And so what this means is if you have a higher pressure, then you're compressing the gas and you're going to have a higher number density than normal, and that means that the mean free path of the gas is going to be lower. And if the mean free path is lower relative to the length scale, then you're less likely to be in a regime where these nanoscale effects are important. So as a calibration, we're going to use the value of a Knudsen number of about 0.01 as a boundary between what we're going to call the continuum flow regime, so a regime where we can use the classical Navier-Stokes equations to describe the flow, and what we're going to call a slip flow regime, where we're going to be able to modify the Navier-Stokes equations for a pipe to account for this slip. And then if you go down to a Knudsen, or go down in scale or down in density, having a more rarefied gas such that the Knudsen number goes up, then you go into regimes where, for example, you really need to model the flow at a molecular level and consider the true interactions and attractions between the molecules. But in our case, we're going to operate mostly in this regime, and we're going to talk about how we can capture this phenomenon of slip quantitatively and then use that to understand its effect on things that we remember from macro scale flows, like what's the pressure gradient through a pipe, what's the flow rate, and things like that. And so, for example, if we look at a characteristic length scale here, so now L is d, it's our pipe diameter, and this is in microns. So if we have a pipe diameter of about 1 micron, 10 to the 0, and we are at atmospheric conditions, then we are in the regime of slip flow. So that says if you're flowing air through a pipe that's 1 micron in diameter, then you have to consider that there is some slip between the fluid and the walls in order to have an accurate prediction of the flow through the system. If instead you have a pipe that's, say, 10 microns diameter or 100 microns diameter, so maybe now think of a glass capillary that might be used for electrophoresis, then you are in the continuum flow regime, and we can, with pretty high accuracy, apply the same equations that we would have applied in regular fluid mechanics with the no-slip condition. So that says that most micro devices under atmospheric conditions are totally fine in a continuum regime, but when we get into the nanoscale regime, we have to consider these effects when we model the flows. So our ability to think about the origin of slip and how that relates to the properties of the gas, it can come from this basic model of particles or molecules in a box that we've seen before. And so for now, we're going to consider that our gas is an ideal gas, and we'll just spend a minute talking about how we can define the mean free path for a gas, or how we would get a value for the mean free path depending on the properties of the gas and the conditions of the flow, like the pressure and the temperature. So we saw on the previous slide that we're defining our Knudsen number for gases as the mean free path divided by our length scale, or lambda divided by D. And according to the ideal gas law, which we all know, there are many forms of the ideal gas law, but the one we're going to use now is that the gas pressure is equal to N, which is our number density that we defined previously, times Boltzmann constant Kb, times the absolute temperature. And in this case, we can say that Boltzmann's constant is 1.38 times 10 to the minus 23 joules per Kelvin. And a typical value for the number density is, say, about 2.7 times 10 to the 25 molecules per cubic meter. So if we assume that we have, a cubic meter of molecules, and we stop time and we look at the positions of all the molecules and we calculate the average spacing between the molecules, then we can say that we have a mean molecular spacing, which we're going to call delta, which is, say, approximately equal to 1 over the cube root of the number density, which we'll say is approximately 3 times 10 to the minus 9 meters, or 3 nanometers. And if we compare this, for example, to the molecular diameter or the atomic diameter of the gas, depending if it's a monatomic gas or a diatomic gas or something like water vapor, then we'll call this small d, which we'll say is about 10 to the minus 10 meters, or 10 to the minus 10 meters is about an angstrom, just as an approximation. So based on this consideration, we're going to say that we're dealing with dilute gases. And the definition of a dilute gas is one where delta divided by D, or the average spacing between the molecules divided by their diameter, is much larger than 1. So in this case, it's about 30. And that just says that the collisions between one molecule and another molecule are mostly just 1 and 1, not 1 and 2 or 1 and 3. So you mostly have single atom collisions. And the mean molecular spacing is not the mean free path. So the mean molecular spacing is, at this instant in time, if we measured the distances between all these molecules. The mean free path would be the distance that any molecule travels before it hits another one, which is going to be substantially larger than the average spacing between the molecules when we stop time. So now with this assumption, we can look at the formal definition of the mean free path. So from the theory that describes gas behavior in this way, it's stated that the mean free path lambda for a gas is equal to 1 divided by pi times d squared times n times the root of 2. And as we know, this is our number density, which is a function of pressure. In fact, it was in the ideal gas law we defined on the previous slide. And this was our so-called hard sphere diameter, our molecular diameter. And if we substitute the ideal gas law in here, just substituting n from P equals n times Boltzmann's constant and temperature, we get this is equal to Boltzmann's constant times temperature divided by pi times the pressure times the hard sphere diameter squared times the root of 2. So given these, if we knew the pressure, the temperature, Boltzmann's constant is always the same, and knew our hard sphere diameter, this would let us calculate for this dilute gas, which is good for the gases we're going to consider, the mean free path under conditions. And as we would expect, if with temperature at the same pressure, the gas is going to expand. So if the gas expands, the mean free path gets bigger. If the pressure goes up, then the gas is compressed, and the mean free path goes down, so the molecules travel a bit less as before they collide with another one. And remember, we defined that on our chart before, that if the Knudsen number is, say, less than 0.01, we say we're in the regime of continuum or no slip flow. And if the Knudsen number is, say, less than 0.1 and greater than 0.01, then we're in the slip flow regime. And then if the Knudsen number is, well, we're going to say greater than 0.1 and less than 10, then we're in the what's called the transition regime. And there aren't really a lot of clear theories of how to treat the transition flow regime, other than it's somewhere between this case where you just have to think about slip at the wall to a case where you're beyond a Knudsen number of 10 and the definitions of macroscopic properties break down. Like you need, just as we saw for transport, like to define resistivity of a material, you need to have enough size, enough collisions, enough scattering. And the same thing occurs with, for example, defining the viscosity of a gas. If you don't have so many molecules and these interactions are so important, it's hard to assign a continuum property. So if we were to calculate lambda, say for air, and we said, what's the mean free path of air at 1 atmosphere at 300 K, so pretty much air inside this room, then we would get that lambda is about 65 nanometers. So to get a Knudsen number of, say, greater than 0.01, we are definitely in the, or less than 0.01, we're definitely in the microscale regime. However, if we say we're at 0.001 atmosphere and 300 K, so something that would be considered to be a very, very light vacuum in the context of processing materials, then lambda is bigger by a factor of 1,000, 65 microns. So then for our lambda over d to have Knudsen number then less than 0.01, we need d greater than 6,500 microns, or 6.5 millimeters. So at that slight vacuum, even a pipe that has like half a centimeter in diameter is going to have these important effects. And as you can imagine, in any like practical vacuum for materials processing, you're in the free molecular flow regime pretty easily because those vacuums are pretty low. And this is just another chart that looks at how the flow regimes change with scale. And now we have the Knudsen number on the vertical axis, and we have the length scale on the horizontal axis, or h. And so I think this is kind of like, you think of it as a pipe diameter or the height of a channel or something. And it's giving the boundary between what they're calling MEMS and nanotechnology as being at a length scale of 100 nanometers. And this is interesting because it plots devices that are made that process flows and deal with flows, and it shows that a lot of microchannels and micropumps, which are in the size of many microns, end up in a continuum regime. A lot of MEMS devices end up dealing with things like valves and nozzles and accelerometers are in the slip flow regime, and things like hard disk drives where the read-write head rests on a very thin film of gas, and in fact using that gas as a cushion of air that really affects its dynamic properties and how fast it can move is really down in the nanoscale size regime. So even though it's a microfabricated device, it's relying on an understanding of the dynamics of flows at very small length scales, and often requires a lot of specialized flow modeling to consider how the gas interacts with the surfaces. But the take home here is that a lot of MEMS devices and materials into the nanoscale require consideration of these interactions and consideration of slip.
So how we're going to think about slip in a quantitative fashion is we're going to look at the boundary condition between the fluid in a channel and the wall. And we are going to consider how our modeling may be a bit different if we now say that there's not the case of no slip, but there's some slip between the molecules and the wall, or there's some relative velocity. And so in the case of when we previously in fluid mechanics solved the pipe flow equation, we said that the shear stress is equal to the velocity gradient at the wall, and that the velocity at the wall is equal to 0. And that's the case over here. And now we're going to apply a velocity boundary condition at the wall that allows us to have some slip between the fluid and the wall. And we're going to apply a slip coefficient, which in this case is called B, and in our derivation will be called S. And that'll say that the velocity at the wall, in this case they're saying it's h over 2, and in our case when we do it for a circular pipe we'll say it's r, the radius of the pipe, is equal to this slip length B, or the slip coefficient S, multiplied by the velocity gradient. And you can see that in the case of where you have partial slip, the physical interpretation of this slip length B is it's the depth into the wall that you would have to go in order to reach a 0 velocity if you extended this velocity gradient into the surface. And an absolutely limiting case, which doesn't really happen, but there are cases where there's a lot of slip, is where you had perfect slip, and in this case B would be equal to infinity, and in that case the velocity profile would just be straight, because there would be nothing retarding the motion of the fluid at the wall. And so in both cases of gas and liquid flows, we're going to apply this type of boundary condition where we're going to have a coefficient. And the difference in the way we're going to determine that coefficient is for a liquid flow, we're just going to be able to say the slip length is a certain value, which might be determined or calculated from experiments. In the case of a gas, we'll be able to determine the value of this coefficient based on the mean free path and knowledge of how the gases interact with the particular wall material. And that'll give an idea of how much slip there is between the molecules and the wall. It's a lot easier to think of a liquid, moving smoothly past the wall than it is a gas, where there are a lot more collisions and a lot more space between the molecules. But this treatment will apply to both cases and will let us be able to predict the flow rate in both cases. Okay, so let's start and work this out for the simple case of a pipe flow. So we're going to consider a pipe that is just a cylindrical pipe, and we're going to say that the flow down the pipe is happening in the z direction, and the pipe has a central axis, and the distance from the central axis is the coordinate r, and the pipe has a radius r, and like we said before, the diameter will be d. And we're going to assume that we have the case of steady, fully developed flow. Which means, importantly for us, that the pressure gradient, dP dz, is constant. So we're not considering any transients or changes in the conditions here. And we'll have this nice parabolic, azimuthally symmetric in the theta direction, velocity distribution. And we're basically going to solve what this is depending on how much slip we have at the wall. So we can state the Navier-Stokes equations for this case. And the Navier-Stokes equation is kind of like the Schrodinger equation, defined for a very complex case to consider variations in density and pressure and velocity in space and time. And it's difficult, if not impossible, to solve those exactly, if not only for very specialized cases. But in the case of this flow, which is a one-dimensional flow, meaning we have V varying in the r direction only, or the profile is self-similar with r and is therefore symmetric in theta, we only have variable terms in the r direction. So our reduced Navier-Stokes equation for this case says that 1 over the viscosity times the pressure gradient, dP dz, is equal to 1 over r times d by dr, r dv dr. And so now we're going to integrate this equation. We just have one variable because dP dz is constant as we defined before. And we can apply a boundary condition and we can solve for the velocity profile. So if we pop the r on the left side, or on the right side up to the left side, we have r over mu dP dz equals d by dr, r dv dr. And because we have two derivatives in r, then we need to integrate twice. So we can just integrate both sides twice, and because they're indefinite integrals, we're going to add constants. So the first time we get it, we'd get r squared divided by 2 mu times the pressure gradient, and we can add an arbitrary constant to one side, which will account for both sides. And the integral of the first derivative is just the first derivative goes away, is equal to the integral of r dv dr. And we can take the r from the right side and divide it out on the left side. So now we can just take the integral of r divided by 2 mu dP dz plus our constant divided by r equal to the integral of dV dr. And if we integrate this once more, we'll get now r squared divided by 4 mu plus our constant times the natural log of r, because the integral of 1 over r is the natural log of r, plus another constant d is equal to v, and it's v of r. I just had v up in the previous lines to save notation. So this says that our velocity profile as a function of r is this parabola, r function of r squared, plus c natural log of r plus d. And right away, we know that we need the velocity at the center of the pipe to be finite. And the natural log of 0 diverges, so by that we can immediately say that our constant c needs to be 0. So we can lose the term that's a function of c. And then if we apply the no-slip condition, so we're going to apply slip first, and then no slip, and then we're going to apply slip, we know that the velocity at r is equal to big R, at the wall is equal to 0. So that just tells us that the particular solution to our equation has the constant d being equal to minus big R squared, the pipe radius squared, divided by 4 mu times the pressure gradient. So then our final answer for this, for the no-slip case, and I'm going to call this V n comma I. No slip is the n, and I is incompressible, is equal to, and a function of r, is equal to minus 1 over 4 mu times the pressure gradient times the quantity r squared minus r squared. So velocity is maximum at the center when little r is equal to 0, and velocity is 0 at the wall when little r equals big R. And then if we want to define the flow rate, then we can give it the symbol Q, which is typically used for flow rate. And the flow rate is just the integral of the velocity over the area. So we can just take the integral over the area of V of r times our differential area dA, and the differential, the dA of a circle is just 2 pi r dr, because we can integrate the thetas right away. So this would be just equal to 2 pi times the integral from 0 to r to capture our velocity distribution in the r direction times r E of r dr. So we're not going to go through the math to save some time, but this would tell us, if we just substituted our velocity distribution in here and did the integration, that the flow rate is equal to minus dp dz times the quantity pi r to the fourth divided by 8 mu. And the pressure gradient is negative because pressure drops as the flow goes down, so we have a positive flow rate. And as the pressure as the pressure gradient gets bigger, we can drive more flow through the pipe. As the radius gets bigger, we can drive more flow through to the power of 4. So that's really indicative that the flow resistance, or the amount of flow we can pipe through, is strongly dependent on the radius. And as the radius gets smaller, with a very, very strong dependence, you require more force to counteract the friction at the wall. So this, if you've taken fluid mechanics before, this should seem like a total recap of one of the introductory things that's done. And the reason why I went over this is we want to follow exactly the same procedure to derive the equation if we have a non-zero velocity at the wall. So now we're going to go back to where we had that unknown constant c, and we're going to apply our slip condition, and we're going to determine what c is if we have slip. So now let's consider the case where our velocity at the wall, v at r, is equal to our slip coefficient, which was b, was the slip length on the previous slide, times dv dr at the wall. So the velocity is going to be proportional to the slip coefficient times the gradient. And before we solved for the value before, we had v of r being equal to 1 over 4 mu dp dz times little r squared plus d. And so now, if we take the first derivative, or if we evaluate it at, we take dv dr, then we have this as being equal to 1 over 2 mu dp dz, and the d goes away. And so now we can say that v of r is equal to minus s over 2 mu times dp dz, which should equal to the substitution of r here, or 1 over 4 mu dp dz times r squared plus d. And there should be an r here and an r there. Sorry, was that clear? So this is just this. And this is this, substituting there. So now, if we solve this for D, just rearrange the previous equation, we get the answer of minus 1 over mu times the pressure gradient times the quantity r squared to 4 plus SR divided by 2. I'll write the S a bit more clearly. There. And then if we go ahead and we substitute this in our original equation and then collect the terms, we would get that the velocity for slip flow, S, in the case of still incompressible flow, is minus 1 over 4 mu, and we still have the pressure gradient times r squared minus little r squared plus 2 SR. So the slip coefficient, like the slip length, has units of length, and therefore we can see that all that's effectively been done by doing this is we've added another term here that corresponds to the contribution due to slip. So if our slip length or slip coefficient is 0, this term goes away and we have the same equation we did when we did no slip. And it means that this is effectively, quote, adding extra velocity to the whole profile. So slip has the effect that at the same pressure gradient, you're going to be able to push more flow through the pipe. And it's like taking all the fluid in the pipe and adding a constant velocity to all the streamlines. And that is just quantified by this term here. And so we can go through the same exercise we did to calculate the flow rate. So if we determine the flow rate, Q as the integral over the area of V of R dA, then I won't go through the procedure, but it's all in the written notes that I've posted. We would get the answer that the flow rate for the slip incompressible case is minus pi dP dz times r to the 4th divided by 8 mu, what we had before, plus SR cubed divided by 2 mu. And then if we rearrange this so we solve for the pressure gradient, we would get just equal to minus Q divided by pi over mu, and then r to the 4th divided by 8. I just pulled out the mu, plus S r cubed divided by 2. So we can see that now, just in a different way, if we keep the flow rate constant and we increase the amount of slip, then our denominator is going to increase and the pressure gradient is going to drop. So to push the same amount of flow through the pipe due to slip, we're going to need less pumping power. Okay, so I have a bunch of extra blank slides here. So practically, let's see how much of a difference this makes, because we haven't really said, well, how much does S affect it? You can see that if S, the slip length, is on the order of the size of the pipe, then it will be just like having R in there, or D over 2 in there, and then it would make a big difference. So these are some calculations I did a while ago for flow through methane at high temperature through a microchannel. So this is a 5 micron diameter pipe at pretty high temperature, and the gas is methane, so it's a bit different than air, but I think if I remember right, the mean free path in this case is about 250 nanometers. So the mean free path of methane is about like air at room temperature, and this is about 4 times room temperature, so the mean free path is like 4 times 65 nanometers, so about a quarter micron. And what I'm plotting here is in the case of a constant flow rate, so 0.1000th of a cubic centimeter per minute through this little pipe, the velocity as a function of radial position from the center to the outside. So here I'm posing the same flow rate q. So the integral under the curve is going to be the same, but you can see that in the case of slip, the velocity at the wall is, say, about 20% of the maximum velocity in the center. And it effectively changes the resultant shape of the flow profile. And the different curves here, this represents the case of slip flow, and then this represents the case of no slip flow. And I was learning computational fluid dynamics software at the time and trying to compare the result from the analysis to the result with the Fluent software if I applied this slip boundary condition. So if I just modified the condition at the wall, and you see in this case that the analysis and the computation agree pretty well. And there's also another model here called the unified flow model, which I was looking at that we won't get into, but that's one that's proposed in the Microflows book if you were to go on. But it just tries to consider different parameters and let the applicability of this approach go to higher Knudsen numbers, so to what they call the transition regime. But we don't really need to consider that for our understanding here. And so now here's a case where I have the same conditions and the same flow rate, 0.001 SCCM, but I've increased the diameter of the pipe tenfold. And now I've gotten into a regime where the slip really isn't important. So the velocity profiles are almost identical in all the cases. There is a difference of, say, only a few percent. So this is a case where applying the no slip condition would have been almost entirely appropriate. So now let's look at what this means for the pressure gradient, the pressure drop through the pipe. And so now, if the flow rate is always the same, the total amount of flow we're going through, now we're considering, for example, if the inlet pressure is always the same, what's the difference going to be in the outlet pressure? And this is plotting the case of the pressure gradient, or the value of dP dz in pascals per micron. So 1 atmosphere is like 100,000 pascals, and 1 micron, this would just be in terms of the length of the pipe, as a function of the pipe diameter. And so you can see that the departure in the value of the pressure gradient for no slip and for slip, it gets bigger, as you would expect, as the pipe diameter gets smaller. So as we go into a case of having more rarefaction or a higher Knudsen number, the difference between the no slip and the slip cases gets bigger. And so in this case, if we had a pipe that is, say this is 1 micron diameter, I think, to 10, we would have almost a 50% difference in the pressure drop through the pipe. And it says that the pressure drop in the case of slip flow would be a lot lower because the molecules are slipping. And if we go up beyond 10 microns, kind of down to the case on the previous slide of 50 microns, it's almost the same. And this is just a plot of the equations for pressure drop that we had derived on the previous slides, except I defined S, the slip coefficient, based on what I'm going to talk about now, based on the relationship between the mean free path of the gas and how it interacts with the wall. And that's how we apply the case of the gas to these equations. But it's just having the known value of S and plotting those equations as a function of the geometry. So the formal definition of the slip coefficient for a gas remember we called it S, is the ratio mu over epsilon, which is said as the ratio of the internal friction in the gas to the wall friction. So the viscosity of the gas is the gas is resistant to the fluid's resistant to deformation by shear. So it's like the internal friction of the gas. And now this parameter epsilon is a parameter that we're going to call the wall friction, or how much friction the gas feels when it interacts with the wall, because that's kind of what slip is. If there's a lot of friction between the gas and the wall, then it's not going to move very fast when it hits the wall. But if there's less friction, then it's going to move freely past, and there's going to be a lot of slip. So without going into the details, I can just tell you that this ratio, mu divided by epsilon, is defined as mu over the density of the gas, rho, times the quantity, which is the square root of pi divided by 2 times the universal gas constant times the wall temperature, or just the temperature, multiplied by the quantity, 2 times a parameter sigma v divided by sigma v. And sigma v is what's called the tangential momentum accommodation coefficient. Kind of a mouthful. And we can write out it as the difference between the incoming tangential momentum of the gas molecule minus the outgoing or reflected tangential momentum divided by the incoming momentum. And let's think about that physically in a couple of limiting cases. One where the gas molecule comes in at some incident angle and hits the wall and basically reflects perfectly. This is like specular reflection of the gas molecule. So this is the case where we'll say the reflection is specular and the tangential momentum accommodation coefficient is 0. So here is where we would have the most slip. And in the other limiting case, if the molecule comes in and it loses all its tangential momentum or all its lateral momentum and goes straight off, so it's just like going from an angle bounce to a vertical bounce, so it's totally stopped in the streamwise direction, then this is what we'll call diffuse, and this is the case where sigma v is 1. And it turns out that for most gases, our momentum coefficient sigma is between 0.75 and 0.85. And this is what's talked about in a bit of detail in one of the papers. And they actually describe, as we'll see in a minute, how they characterize the slip flow through microchannels and make such high precision measurements that they're able to calculate what this actually is. And so you can look into sources and you can look this up for various gases, but if you're doing this kind of calculation, a value of about 0.8 is pretty accurate. So when I did that plot in MATLAB, I think I took a value of about 0.8 for methane, which is the best one I could find, and then use that to derive the slip parameter, the slip coefficient, and then put that in the resulting equation for the flow rate and for the pressure gradient. And another thing that is important to consider is that because, as geometries get small, we have this great amplification of a pressure drop. So to force the same flow, remember it's like 1 over r to the 4th for our dp/dz, then you can get relatively high pressure drops when you're putting flows through small pipes, meaning, and compressibility, of course, is only important for gases and not for liquids. So we could go through additional exercises that would let us derive the equations for compressible flow through these channels and compressible no-slip flow and compressible slip flow. And basically, we won't go through it, but what you do here is, when we derive the volume flow rate, we were conserving volume flow and we weren't worried about density. And in the case of compressible flow, volume flow is not conserved. Like the volume going in can be different than the volume going out, but of course mass flow is conserved, so you just apply conservation of mass instead of conservation of volume, and you have a density gradient through the pipe, and that, with some more involved math, will let you solve for compressible flow in the channels. And you can see that in the Archillic paper if you want, and I have a bit in my notes about it. And anyway, what I did here is I took the same geometry of having a 5-micron diameter circular pipe with methane at 900 C, and incidentally I was looking at this for growing nanotubes in microchannels, so this is a type of condition that you might use to grow carbon nanotubes, as we'll see later. And here I was calculating it for a fixed mass flow, so equivalent to the volume flow but normalized for mass flow. And so now we have cases of no slip flow and slip flow. So the two, the red dashed line and the blue line versus the black lines, and compressible and incompressible flow. And so if we start in the case of no slip incompressible flow, up here we have the largest difference in pressure from the input of the channel to the output of the channel. And if we first apply slip, then we see that we have a reduction in the pressure drop because of slip, as we saw before. And then we apply compressibility, where we have slip flow and compressible flow, we have a further reduction in the pressure drop. So the fact that the gas is compressible and the density changes manifests itself in a further reduction in the pressure drop, and for a particular pressure drop, a difference in the flow rate. So one of the ways this is important it can be important in a number of ways, but for microfluidics, if you have such a small device, it's very difficult to measure flow. It's typically done where you apply a certain pressure to a device and then you expect a certain flow to go through the device. And because of these big differences, the amount of flow that's actually going through can be different, so that can make a big difference in the practical operation of the device. And for note here, we're looking at PSIs of, say, 5 to 10, which is like maybe 1/3 to 2/3 of an atmosphere over a distance of a couple millimeters. So say 2,000 microns. So if you have a microchannel that's a couple millimeters long on a few microns in diameter, you can have practically quite high pressure drops. So just one more slide before we go, and then I'll pick up with the rest next time, which is mostly talking about examples from the literature, examples from the papers you've read. But to conclude, I think we should learn a bit about what the molecular origins of slip are. Basically, what determines the velocity at which the fluid moves moves over the wall. We had this momentum accommodation, but basically what determines how much momentum is transferred. So we need to consider, as we did in the case of wetting, think about how the molecules in the fluid feel the molecules in the wall. So if in the limiting case where there's a lot of slip, that can mean that the interactions within the fluid are stronger than the interactions with the fluid on the wall. So for example, if you have a surface that's hydrophobic and you're flowing water through it, you can have more slip because the water doesn't like the wall and the wall doesn't like the water in a general sense. Another means of creating slip is that the roughness of the wall itself can trap gas molecules that are dissolved in the liquid, and that can create kind of a lubrication layer. So there's actually a very small cushion of air at the interface between the fluid and the wall, and that can reduce the amount of friction that the liquid feels as the liquid is moving through through the channel, kind of also analogous to having like a few contact points and that liquid only feeling the high friction at those contact points. This is also practically important for things like designing surfaces for drag reduction for underwater vehicles and for ships, and there's a big difference here in the behavior at low Reynolds number and high Reynolds number. These kind of lubrication layers tend to break down when the flow velocities are higher. And then we can also consider that the actual physical interaction between the fluid and the wall is like a diffusion process, or like hopping of molecules along the surface. And every time the molecule interacts with a certain site on the wall, there's some attraction and interaction, and the fluid above it is kind of pushing it along, and the wall is pulling on the molecule, and the slip length and this behavior can depend on the temperature based on the overall transfer kinetics of the process. And there are cases, for example, where you can observe if there are strong interactions between the wall and the fluid, as I alluded to before, that you actually get stratification of the flow at the molecular level at the wall. So this is a snapshot from a simulation from the reading where it's just plotting the kind of local fluctuations in density. And if you have very strong interactions, you can see that the molecules are strongly attracted to the wall, and their distribution in space is actually altered by these things. So we won't practically consider exactly what this case is, but I just want you to realize the origin of this behavior and how we can capture it using the simple parameter of the slip length. And those are the kind of things that I'm asking about on the first problem of the problem set with application to flow through nanotubes. So we'll pick up with the rest of the examples on Monday, and we'll also talk about electrostatics in fluid flows.